Okay, we begin our study of momentum. And the symbol for momentum is P. It's a lowercase p, and it's in bold because it's a vector. Momentum is a vector, and that's important. Energy is not a vector, but momentum is a vector. And what does the momentum of anything depend on? It depends on its mass, and it depends on its velocity. Okay, no surprise there. If we increase the mass of something, it's going to have more momentum. If we increase the velocity of something, it's going to have more momentum. So that's our definition of momentum. P is a vector, and V is a vector, and momentum is a vector. So next question, like if we want to change the momentum of something, if we want to change something's momentum, that if we want to give it more momentum or less momentum, generally we don't change the mass. That could happen. But we usually change the velocity. So we know to change velocity we need a force. So let's go to our Newton's second law equation. Okay, I hope you recognize this equation. Force is equal to mass times acceleration. Now let me do some writing. So force then is the mass, the acceleration is the change in velocity over the change in time. And if I rearrange this, I get that the force times the time interval is equal to the mass times the change in velocity. So the mass times the change in velocity would be a change in momentum. And so what changes a momentum is when a force acts, and how much it changes depends on how long the force acts. So think about the logic of this equation. So this quantity of force times time has a name. It's called impulse. So we can write out the word impulse, or in some cases we'll just write IMP, and occasionally you'll see a J for impulse, but mostly I will use the IMP. And so IMP equals the force acting on an object times the time over which it acts. That is the definition of impulse, force times time. But the impulse is equal to the change in momentum of the object. So if we write that equation, impulse, which is the same as this, but it's also equal to m delta v, excuse me, which is, we can write it as delta p, change in momentum. I should make these vectors. The impulse is also a vector. It has a direction. It can be positive or negative, or in different directions. Okay, so let's just review this. This is the second important thing. The first important thing is our definition of momentum. The second important thing is how the relationship between force and change in momentum. And so there were two things here. There's this equation. This is called the definition of impulse. Impulse is equal to that. This equation sets the impulse equal to the change in momentum, and this has a different name. This is called the impulse momentum theorem. So let me pause the video and reorganize the screen. Okay, so one more time. These three equations, the definition of momentum, the definition of impulse, and the relationship between impulse and change of momentum, the impulse momentum theorem. I didn't write that down, but that's important. So equation 1, equation 2, and equation 3. And those three equations are all that we're really going to use this week to solve problems. Now, momentum is generally applies to problems where there's a collision. So let's take a look at, okay, let's take a look at this situation. This is a very simple example. Two carts coming toward each other, just like our lab carts, red and blue. They're equal in mass. And, oh, I see one thing wrong with the diagram. You see the spring, it should be in the inside, so when they spring, they bounce off of each other. So the two carts come together. They collide, they hit on the spring, and then they bounce back. Okay, so that's a simple collision. And what we see is that the velocity, if the velocities are equal, then they bounce back with the same equal velocity. So in this situation, the blue cart undergoes a change in momentum. And notice, this has a positive momentum, and it comes back with a negative momentum. This has a negative momentum, and it comes back with a positive momentum. So the momentum of each cart changes. But if we consider the carts as a whole system, the force on each cart is internal. And so the two carts as a system will have no change in momentum. Let me show you what I mean by that. I'm going to pause the video for a second. Okay. So anyway, I lied. I just remembered there were 4 equations. So we have the definition of momentum, the definition of impulse, and the impulse momentum theorem. But the 4th equation is, in a case where there's no outside force acting on an object, if there's no force acting, then the momentum won't change. And so what we saw is that the momentum of each cart changed, but if we take the two carts as a system, there's no outside force acting on it. Why? Because the track is flat, so gravity's not affecting their motion, and the carts are frictionless. So in that situation, we have the 4th equation called the law of conservation of momentum. Remember, we had the law of conservation of energy. Now we have the law of conservation of momentum, which says P initial equals P final. I'll put the vector symbol in. Remember, like conservation of energy, the initial energy equals the final energy. And so let's use this equation to solve the problem of any one of these collisions, and I'll show you several of them in a minute. So if I write this out, the initial momentum is the mass of the blue cart times the initial velocity of the blue cart plus the mass of the red cart times the initial velocity of the red cart. So what is that? That's the initial momentum. That will be equal to the final momentum, which is the mass of the blue cart times the final velocity of the blue cart. Oops, I'm going to run out of space here. Let me move these out of the way. Go back to my writing. Plus the mass of the red cart times the velocity of the red cart, the final velocity of the red cart. Okay, so what you have is you have the law of conservation of momentum, which says if there are no external forces acting on the system of objects, the initial momentum will be equal to the final momentum, and the momentum of each object in the beginning and the momentum of each object at the end have to be equal to each other. So this is the equation that we're going to use pretty much all week solving most of the problems. So this is the fourth equation in our set of equations. Okay, so we're studying collisions, and we have the four equations. And what we're going to see is we have there'll be a wide variety of collisions that we're going to look at, but there's two major types. So let me show you the first one I showed you last time. This is a collision where the two carts come together, collide, hit a spring, you can't see the spring, and then they go off in opposite directions. And in this case, momentum is conserved and energy is conserved, and this is called an elastic collision. Elastic because there's a spring, because it bounces and no energy is lost. So that's one type, the elastic collision. And then here's the other type. So in this situation, we have a cart moving and a cart which is stationary, and the moving cart collides with the stationary cart and they stick together. So when they stick together, this is called an inelastic collision. And what we're going to see is that the momentum will still be conserved, but because they stick together, because it's not elastic, energy will be lost. So I'm going to pause the video and write that down for you. Okay, I wrote this out for you to see. The elastic collision, where things bounce off of each other, means that both momentum and energy, kinetic energy, are conserved. A collision is called an inelastic collision if momentum is conserved, but some or all of the energy is lost. Okay, so all of this is what you need to do the MOPS, and as you start the MOPS, you should email me, and we'll meet during class time if you have questions. And also I'm going to post the lab, and the lab will be, like we've seen over the past 2 weeks, simulations of collisions. So before I leave, and I'll try to I'm thinking about making a video on the simulations that would be related to the lab, so look for that. But before we leave, let's do one problem together, just so you see on the ground how this all works. So let me take this situation and expand it. And then what we have, here's a collision, and it's the two objects collide. So this is before the collision. The two objects are approaching each other. They stick together, and then the bigger object with more velocity, right, the whole thing goes off in this direction. So notice, this is a positive momentum, and the mass times the velocity, it's going to be 4 times 15. So there's 60 units of positive momentum. And then the smaller object, which is only 2 kilograms and 3 meters per second, this is a negative 3 meters per second. So the 2 times the 3 is 6. So there's a negative 6 units of momentum in the yellow box, but there's a positive 60 units in the blue box. And so when you take the initial momentum, let me write that out. So the first cart, right, it's the mass of the blue cart times its velocity, initial velocity, plus the mass of the yellow cart times the yellow cart's initial velocity. That's the initial momentum, right? That's the P initial. And so we have, I'm not going to write it all out, it's just 15 centimeters, 4 kilograms times 15 centimeters. That's 60, notice the units, kilogram meters per second. The yellow, however, is 2 times a -3. This is important, you got to use the -3. And so 2 times -3 is -6 kilogram meters per second. And so the final momentum is going to have to be 54. But the final momentum, notice both carts are together now. So the final momentum will be the mass of both carts, the blue and the yellow, times the final velocity. And there's just one final velocity because they're stuck together. So we have 6 kilograms times the final velocity. Okay, so what I'm going to do is I'm going to divide by, let's just, this remember is 54. And so I'm going to divide the 6 into the 54. I've run out of space, kilogram meters per second. The kilograms will cancel. And so when you divide 6 into 54, pause the video. Okay, I made some space, so there's the V final. It's the 54, which is the 60 minus the 6, and it's divided by the total mass on the final side, and so you get 9 meters per second. So the 15 meters, 3 meters this way, they stick together, this goes off with 9 meters per second. We use the law of conservation of momentum to calculate that. If we calculated the energy of these two things and the energy end, would see that the energy at the end was quite a bit less because energy was lost. Why? Because it's an inelastic collision. Okay, you're on your own. See you soon. Bye.